This is a demo of a multiply instruction and taking the result of that instruction and putting it in registers for the single cycle computer. So run the VinciLab application file mult move mult high and move mult low. This will require you to log on to Vincilogy with your username and password and will take some time to configure and start up. When the UI opens with the tabs, maximize it, and the tabs represent various instruction-based pictures that are related to the multiplication. And then on the right hand side we have lots of tabs which are specific full function descriptions of the logic in each of the blocks in the single cycle computer. So go to the IDE, open the assembly program, mult move mult high and low. This calls a function which writes to register SFR11 and 10, those are multiplicand and multiplier values. The values 15 hex and 17 hex respectively. And then on return executes multiply and writes the 16 by 16 multiply result, a 32-bit value, to register 7 and register 6 when it's available, and then ends the program. So I assemble and transfer to program memory. So the program starts at program counter 0 where it calls the function setup, and I'll step through these because these instructions move data pointer, move special function register to register, etc. I've dealt with in other video demos. You can see on the right hand side the instruction based picture opens in the tab, and when it returns from the interrupt it executes the mult instruction. The mult instruction, there's very little activity here, there's no register writes. Register or special function register. There's no data coming through the operand fetch or the function execution unit. The program counter is incrementing. The opcode here, 7 bits, is shown, and there's no other parameter in the instruction other than mult. And the instruction decoder only asserts one signal, go mult, to the 16 by 16 bit serial multiplier. There are 2 registers which have been written, special function register 11, SFR11 and 10, with the values 15 and 17 hex, which define the multiplicand and the multiplier respectively. And in the multiplier, over 17 cycles, the first registering multiplicand and multiplier, and then 16 cycles which operate on each bit at a time. And the result is output on mult out. And the signal mult done is asserted when the multiply completes. Internally in the multiplier there's a bit count which is loaded with the value 16 decimal and decrements to 0, at which time mult done is asserted and the result is available. So I can single step the instruction, and you'll notice that the program counter is incrementing just by 1. And now the multiply has started execution. This is the next instruction, move mult h. This takes the output of the multiplier when mult done is asserted and puts the value into the register that is defined by the output address, in this case 7. So I'm moving the multiplier output, the high 16 bits, there are 32 bits in the multiplier output, to register 7. This is the opcode, this is register 7 output, and these bits in the instruction are not used. Move mult h instruction is now executing, and it will write to the register bank to register 7. This is the mult out signal, the 32-bit result, but it's not yet ready. It's validated by the assertion of signal mult done, so it's not yet the final result. This multiplexer selects the upper or the lower 16 bits. In this case it's move mult h, which is the upper. This blue star should be on this side, it's just misplaced in the drawing, because this signal, which is asserted by the instruction decoder, select mult out upper word, is asserted. So it selects the upper 16 bits through here. Check mult done is asserted by the instruction decoder on move mult h or l. So it selects that 16 bits through here too. The other paths are not illustrated here because this is just about the multiplier. And the output is currently 0. But the write will not yet take place because the write only happens when reg write is asserted and mult done is asserted. That's all handled internally in the write back. The program counter does not change because mult done is not asserted yet, and the signal hold PC is asserted, and therefore it selects this path which takes the current program counter value and maintains that value. I can now look inside the write back, as in the details in this block here, by clicking on the tab browser and then looking at the right back options that are down here. And the right back top can be selected by this. So here is the mult out coming through. You can see the star on the asserted side of that multiplexer because of the assertion of this signal by the instruction decoder. Check mult done asserts it through to here. The default on this signal is a 0, so it's selected through to here. Now the value happens to be 0 in this particular case, but even though the data is coming through from mult out, it won't actually execute a write because the enable signal into the register write is determined by a number of signals. One is select rbank, one is reg write, one is check mult done, but it will wait until mult done is asserted before it actually does the write. And by that time, this value will have changed because the multiplier will provide the final result. So I can go back to the tab browser. Now I can go into the multiplier itself from the tab browser and show what's happening in here. This is the result of the multiplier. It's a combination of these two registers. The first register is loaded, just to summarize, with the multiplier when go mult is asserted by the single cycle computer. And this register is used and shifted on every cycle, and the bit 0 is lost, but for every one of those 16 cycles, bit 0 is used to determine in this adder if the adder adds the current value of the upper 16 bits with a 0 or with the multiplicand. So a binary multiply is a series of add shift steps, adding 0 and shifting right, or adding the multiplicand value to the current result and shifting right. The first cycle loads this with the multiplier and loads this with 0. So go mult pulse at the start of the mult instruction, it's asserted. So a 0 goes into here, multiplier goes into here, and every cycle the add occurs, it generates a 17-bit value out of two 16-bit adds, takes bit 0 and uses that as the upper bit into this register and loses the significant bit. All of this occurs under the control of a counter, loaded initially with 16 and decremented to 0. When it gets to 0, mult done is asserted, and the value that currently is in those two combined registers is the value of the mult out. Mult done is maintained asserted until the start of the next multiply instruction, whatever that might be in the program, and that deasserts when a non-zero value is loaded into this counter. Go mult is a signal asserted by the instruction decoder, and a single pulse is generated, go mult pulse, to load this with the value 16 and to select a 0 into here and to select the multiplier into here. From then on in, as long as the bit count is greater than 0, the signal chip enable is asserted and it selects the path from the adder through to the output, or the path here from the shifted and looped back value of this register through to the next state for this register input. So it's a complicated little diagram, but some tests will hopefully illustrate how this happens. I can go back to the tab browser again, and I want to go back to the IDE now. So to go to the IDE, I start again and assemble, load the program, and I will wait until the mult. So just to show you what happens with the breakpointing, this is the instruction 01. I can go into the breakpointing control, enable breakpoints. The first breakpoint that I wanted to stop at instruction 1 and close that. And I can just run, and it will now do all of the instructions but stop there. Probably disable the breakpoint now just for completeness sake, and step to the Movmultl. So this will continue, and I will step. The only thing that's changing here is the mult out value is changing, but it's not been written to this register. You can see the value here changing, but it's not been written to this register until such times as bit count goes to 0 and mult done is asserted. So I'm going to toggle this a number of more times, and you'll see bit count decrementing to 5, 4, 3, 2, 1. And when it gets to 0, mult done is asserted. The value now on mult out 32-bit bus is the value 1E3, which is the result of the multiply of 1 7 hex with 1 5 hex. The upper 16 bits happens to be 0 in this case, but you see that mult done is asserted, and mult done now enables the write to the register. And now also hold PC is not asserted, so the program counter will increment from 2 to 3 to allow the program to progress to Movmultl. I'm just going to look at the tab browser again and then look inside the multiplier, and in this case mult done is asserted because the bit count is 0. this is the value that's coming out. The upper 16 bits are 0, the lower 16 bits are 0, 1, E3, and Mult done is asserted. And let me go back to the tab browser again and into the write back. And in the write back, the upper 16 bits happens to be 0, but now that Mult done is asserted, write reg r is asserted, and the value of the address of register 0 to 7 is 7, so a 0 will be written to register 7 if I step. Now it executes Movmultl. Mult done is already asserted because the 16-bit multiply is completed. In this case, it's writing to register 6. Mult done is asserted, reg write is asserted. So the write will occur and the program counter will increment automatically to the next instruction, which is the end instruction. So if I cycle that, you'll see now that the value on 7 and 6 are 0, 1, E3. Our 7 is zeros. So let me hit reset again. I'll enable the breakpoints again. Run to the Mult instruction. And this time, progress through the multiplier. So initially, go Mult is asserted. Go Mult pulse through the single shot is asserted. It will load this counter. It will also allow a 0 to go into this register, and it will allow the multiplier to go into this register. The multiplier is 0017, so this will change to 0017. This will clear, it's already 0, and a value 16 will apply there. And if I single step and then go back with the tab browser to the multiply, I can leave this picture on by clicking on this and selecting for the tabs not to auto change and selecting the picture that I want to see, which is the one that's there at the moment, but I'll select it anyway. In the multiplier logic, value 16 or 10 hex, 16 decimal or 1000 binary are loaded in this counter. The 0 is loaded in this register and 17 is loaded in this register. Bit 0 of this is a 1, which means that this add MD flag, add multiplicand flag is asserted, and the multiplicand is being brought down here and added to the current value of this 16-bit register to give out the value 0015. This is a 17-bit value. It takes the least significant bit and pushes it across to here. That orange and that orange really should be the same color. And the bit 0 here falls off, and the 1011 becomes the last 4 bits, but the upper bit becomes a 1. So if I single step again, you can see that that 1 moved to here. The next bit here is also 1, and so is the next. So there are 3 adds of the multiplicand starting off, and they affect this register, but there's a transfer of bit 0 across on each of the cycles. So I'm going to step twice more, and now there's a 0 here. So in this case, there's no add of the multiplicand. There's an add of 0 to the current value in this upper 16-bit register. Then on the shift, the least significant bit of this is a 1, so now it's again adding the multiplicand through to here. You can see the selection of this multiplexer because of the assertion of that. And this continues until such times as this count goes to 0, and the result of the combination of these is the final mult out. And what was loaded into the multiplier register, this one here, will all have been shifted out to the right, and 16 shifts of this bit would have occurred. So single step right down to when the count is 0, mult done is asserted, and this is the result value. Go back to the tab and go to write back. In this case, it has now progressed to Movmultl output, and because the result is ready, write reg r is asserted, and the result comes here. Just to complete the example, I'll come back now and I'll move the data pointer and put in a value 115, and I'll put a value 117 here. I won't change the comments. I'll compile the program again. Run until breakpoint. Now I have the values 115 and 117 in SFR 11 and 10, and I'll single step and tab browse to the multiplier. And as I single step now, you'll notice that the upper 16 bits begins to be populated with non-zero numbers because this is a larger number than before. And now it's at the Movmultl instruction, which it repeats so many times until the count goes to 0. So I'm going to go to the tab browser and go to the write back. And in the right back you'll see now that there is non-zero value on the upper 16 bits of the multiplier out. So you can see it's 25 currently. If I step again, it's 12. And so it's changing, but the write will not occur until Mult is asserted. When that is asserted, the final value up here happens to be 0001, and it will write to register 7. It does. And the last value is 2D. E3 will write to register 6. That's the end of the demo.